that's loud. Okay, so I know everyone is pining for the bar, and we're a bit late, so I'll try to keep it brief. But I wanted to show this because I was actually on the antenna plane, and I have to show off a little bit. Of course, you take a selfie when you're on that kind of impressive antenna plane. But the idea is that we will get this unprecedented high-quality data set from EISCAT 3D. It will, if we get the funding, as you heard, it can collect vast amounts of data. And we want to try to use this. Actually, we have a hackathon with EISCAT in November, where I will hopefully try to run a Meteor experiment if we can get everything working until then. There are some kinks to work out, but if we get that working, that's a great step on the way to actually get Meteor measurements going on this. But one of the things that really, how do you say, came to me when I started thinking about what to do with this data set is that to really utilize this to the fullest, of course, we can just look at the radar data and do lots of interesting things with just the radar data, but we can do so much more if we also have multimodal measurements. So I started looking into a little bit, okay, what kind of multimodal measurements can we do? So with the optical systems, we have two now, unfortunately, mostly non-functional Meteor cameras in the vicinity. We have one in Kiruna, one in Abisko. The one in Abisko, I think, died a few weeks ago. And the one in Kiruna has given me quality. I think it's a dome issue or something. We have an infrasound network that has been utilized for several years. We don't have any dedicated spectroscopic measurements. That would be very cool to see with this kind of radar data in the future. We do have ALICE4D, which is for aurora. So it's for auroral tomography. So it has very narrow interference filters. And they do have filters specifically for meteor emissions. So we could also use that to get some very photon counting like emission bands, simultaneous measurements. There are lots of trail radar measurements. We have the Nordic Meteor radar cluster up there. There's also a bunch of other instruments like ionosondes, lidars, magnetometers, and such like that. So a little bit on the side, I'm really a radar person, but I thought that, okay, we need to get some Meteor cameras around EISCAT 3D. Because it would be great to be able to have simultaneous optical radar detections. We could start doing meteorite recovery in northern Sweden because it's quite a big area. It's humongous because I literally drove now for the first time ever in my life across Sweden, and I could, if I just drove the other way, I could have gotten to like Berlin, I think. So it's a lot of area to cover. And it would be great if we could start doing some recovery there too. And then while we were looking into this Meteor camera upgrade, we realized that there's lots of other sky phenomena that these Meteor cameras could actually record for us that will be super useful for other research topics like pulsating aurora, polar stratospheric clouds, noctilucent clouds, and satellite tracks. Okay, so the plan, let's see if this works. If I just hover over here. Yeah, so here we see, like you saw before, the EISCAT 3D sites here. And we plan to put some AllSky7 cameras in all of these camera dots here. So we have already put one on top of the institute in Kiruna. I'm probably gonna drive in a few weeks up to Abisko and install one there. We have a few other ones. We have one in Umeå. We're gonna put one in Lycksele, and then we have gonna scatter a few ones over here. And if we have the availability, hopefully we will fill in this area too, so that we really have good coverage. So how is the plan going? Well, I just downloaded some data, and this is from just a week ago with some aurora in the background. Unfortunately, I tried to get a meteor crossing the aurora arc. I didn't find any, but I see a little bit of aurora in some of these at least. So the cameras are working. We don't really have the processing up yet because there are some issues with like what we can actually plug into the networks at different places. So and we also need to write some custom station keeping software for research infrastructure reasons, and that's not done yet because this is my main topic is still radars. So when I have time, I try to work on this. And then is what the rest of my talk will be about, which is we need to correlate this optical data with the other instruments. So we really need some absolute timing of these. So some stuff we tried. We tried setting the time on the IP camera, and it seemed like they drift several seconds over the weekend when we left them, which was not good. We tried enabling some timestamps in the video streams. The firmware just seemed to ignore what we did and didn't do anything. That was a little bit weird. We tried to use the disk write time, but that introduces a lag because we have no idea what the lag is between the camera and the disk. So we just thought, okay, what about an external calibration source then? So basically this is the same idea as apparently stellar occultation observers have used for decades, which is you have LEDs that are GPS synchronized. So let's see, this is the pointer, right? Yes. So this is how the AllSky7 is currently set up. You have some station computer and local network. You have your network switch and your camera inside the dome. So we just added a little bit of a Raspberry Pi in the middle, where we have a LED driver board and a LED, and we also put some temperature sensors in there. And then on every station, we're going to put one of these cameras, since it's a scientific observation station. We already have an NTP Stratum 0 server. So we basically have a GPS receiver right next to the computer. You could also just plug a GPS receiver directly into the Raspberry Pi and get a Stratum 0 NTP server if you wanted to. So this is what it looks like. It's a bit weird. You just put a bunch of LEDs next to the cameras and they blink with the GPS time. It's a very analog solution and I kind of like it. So here is, we built this first prototype where we just stuffed, whoop. Oh, what did it do now? There we go. Where we just strap these so that they're just outside field of view. And through the valiant effort of my colleagues in Umeå who climbed up onto the roof, they had to wear helmets. They were allowed to skip the harness equipment. So we got it onto the roof. And here is what one of the calibration signals look like. So you see this red blink. And that's just the minute in time binary encoded into the blink. So if we extract we just choose a few pixels and then just plot the red channel, you get a binary code of what minute it is in GPS time. It's like very brute force, but it works. And then we can cross-correlate this, of course, and get some time. So first, I try to correlate it with the file name time. Didn't work at all. This looks horrible. And I think that is because FFmpeg can't really handle microseconds. That's a shame. But we switched to checking the file write time. Works better, but we have this weird stuff here. And that's because of what we heard from Detlef earlier today about this varying gain. So now I'm not going to show that, but basically what happens here is that the camera completely oversaturates and overshoots, and everything looks like a rice bowl for several seconds. So now we are modulating the strength of the LED based on how much gain the camera has. But when we do that and filter a little bit, we get this really nice sort of calibration constant. And we also get the drift of the cameras. And this drift is approximately what we saw in the clock drift of the cameras. So this sort of fits very well together. So now we should get sub-frame timing. So every frame we should know it within a few tenths of milliseconds, 2 milliseconds. And yeah, that's it.
So we have time for a few questions. Jerry.
How faint meteors will EISCAT see?
Faint. That's, I mean, we will go down to micrograms. So I don't know what that would be in visual magnitude though, because we see the plasma. So actually we did some telescopic observations with Tomoe in Japan. And do you remember which, Johan, do you remember which magnitudes we got down to? I don't remember. With Tomoe and mu radar.
Yeah. I mean,
was it minus?
Even this 105 centimeter telescope didn't see all the
No.
meteors. So.
Yeah, so I don't think we will.
Probably very faint meteor.
Very faint, yes.
But if we can get spectra from the brighter ones, we will see them too.
Yes, yes, of course.
It's not necessary to see them all.
No.
Thank you very much. Very interesting. Do you consider, or did you consider to, I mean, if the triangle is only 120 kilometers side length, did you consider to use a kind of triple camera array facing the middle point or something like that to have higher accuracy, higher spatial accuracy and resolution than, for example, with the AllSky7 system?
Yes, so that's really the next step. Is the idea that, because this will cover a much wider area,
Yes, of
and
course.
I mean, as you also heard, like photometry is not easy with this. So probably now we have this thing, so we can do like the AllSky thing. We can cover a very wide area. We can get the dual technique measurements, and then later on we will add more specialized instruments that will just check like in the common volume. Because also since EISCAT 3D is a ionospheric research instrument mostly, it will be pointing everywhere all the time. So it will point over a huge area, usually in its common operations. So we really needed this first step to just cover everything to start with.
We have also an online question that is in fact to the previous talk by Peter Brown. Is there a plan to make transverse scattering meteor measurements with EISCAT 3D to extend to very small meteoroid sizes in addition to the head echoes?
We would be happy to look into that, of course. Yeah. Microphone, he cannot hear you.
Oh, sorry. Yep, of course, we will want to do that. That would be very cool.
Okay, I presume the answer is okay. Well, this concludes then the session 6. So let's thank all the speakers again.